Alright, today we are going to take a look at the number e. So the number e is what's known as the natural base e, or the Euler number. And it's an irrational number about 2.71828, so irrational, it's going to go on forever. Simplifying natural base expressions tells us that we follow the rules as if e was a variable, even though it's not. So we'll get into some of those in just a second. If you want to check out where e is on your calculator, you're using the lowercase e, not the capital E. It's probably a button where you have to hit second first to get there. So when we are simplifying, we are going to treat it like it's an x value, or it's a variable. So we would still take care of that 24 divided by 8. That would give us 3. And then e to the 8th over e to the 5th would be e to the 3rd, because when we divide, we subtract our exponents. So this next one, part B, we would do 2 to the negative 2. And then we would have e to the 10x. While 2 to the negative 2 would be 1 over 2 squared, or 1 over 4. So we could write this as e to the 10x over 4, or 1/4 times e to the 10x. Either one of those would be okay. For C, we have e to the x times 4e to the 2x plus 1. Well, remember, when we multiply, we add our exponents. So 4 is still going to stay out front. We have e to the 1x and e to the 2x plus 1. So 1x plus 2x, that's e to the 3x plus 1. And then this last one, the cube root of 64 is 4. And then the cube root of e to the 9x would be e to the 3x. Because remember, we can write that as 9 over 3, which would give us 3x. I just said try to locate this on your calculator if you haven't yet. Now I'm actually asking you to evaluate with your calculator. So e to the 3rd would be 20.09 if we round to the nearest hundredth. And e to the negative 0.12 would be 0.89. Take a minute and see that you actually get those values when you plug them in on your calculator. All right, natural base exponential function. So y equals a times e to the rx power. So kind of like our growth and our decay functions we've been using, except we have e in here as well. So if a is greater than 0 in both cases, and r is greater than 0, it's a growth function. A still has to be greater than 0, but if r is less than 0, it's decay. That is different than with our growth and decay functions without e. Remember, growth is bigger than 0, not equal to 1 for our b value, or is bigger than 1. Decay is between 0 and 1. In this case, growth is bigger than 0 or smaller than 0. So let's see what it looks like. Graph y equals e to the x power. So just like we've graphed our other ones, my a value, my number out front, is 1. So 0, 1 is my y-intercept. And then we said e to the 1st is about 2.7. So looking at just under 3 there. And it looks like this. E to the negative x power. So that's like saying 1 over e to the x. So in this case, our a value is still going to be 1. So our y-intercept is 1. So I'm at 0, 1, and then when I plug in e to the negative 1, because I want to plug in 1 for my point, I get about 0.37, so 1.37. So in this case, we have a decay function. So e to the negative x power is a decay. All right, transformations. We have y equals ae to the r, parentheses x minus h plus k. That h and k are going to move just like before. We're always going to have our parent function be our original ae to the rx, and then we'll move the h and the k. So here we just have y equals ae to the rx. So we don't have a transformation. So I'm going to be able to plot 0, negative 3. And then I'm going to plot 1. So I have negative 3 times e to the 0.5 times 1, or e to the 1/2. And I get negative 4.95 approximately, so almost negative 5. So at 0, I'm at negative 3. At 1, I'm at negative 4.95. I haven't moved, so my asymptote is still at y equals 0. But that negative 3 made that flip over. All right, so our original here is y equals e to the 0.4x. And then we've moved left 1 down 2. So our original point is going to be 0, 1. And then 1, so we need e to the 0.4 times 1 is about 1.49. We're moving left 1, so I'm at negative 1. Down 2, I'm at negative 1. For this one, when I move left 1, I'm at 0. When I move down 2, I'm at about negative 0.51, so about negative 1/2. My original asymptote was y equals 0. So if I move down 2, my new asymptote is going to be y equals negative 2. So 0, 1, 1.49, looks like that. And then negative 1, and 0, negative 0.51, asymptote at negative 2, looks like that. Okay, the last piece is compound interest. So we talked about compounding annually, quarterly, daily. Even better than that is continuously compounding the interest. The more times you're compounding, the better off you are. So continuously compounded interest looks like this. A equals your principal times E to the rate times time. So PE to the RT. So we have an example here. If you deposit $1,500, you pay 7.5% interest compounded continuously for 2 years. So we want to know our A value. our principal amount is 1,500. And then our E. And then our interest, 7.5%, move that decimal 2 places, so that's 0.075 times, so times 2 years. Notice we're not doing 1 plus that interest rate. That E value is taking care of that for us. So since we're talking money, we're going to round to hundredths. So $1,742.75 is what we would have made after 2 years if we use continuous compounding there. Alright guys, that's all I have for you. If you have any questions, feel free to come in and see me. Otherwise, I'll see you in class.